Hi folks, this is Maths and Physics for you. Today we're going to find the solution of 1D wave equation. And this is in English, obviously. Now the general solution of a 1D wave equation could be given by this equation. This is one format. So we say u xt equals to f of x minus ct plus g of x plus ct. Now u is the displacement, the vertical displacement up. So the displacement of any object that's on the wave which pops up and down. So this is its vertical displacement. And it's given at the point x and at the time t. So we have here two variables. One is x and one is t. So u depends on both x and t. So if x, let's say t is fixed. Here, let's say this is the initial, an example of the initial shape of a wave. Let's say a pulse is given to a string. So at this is at the time t0. At x equals 0, this is the maximum. And let's say we have a point P0 at this location on x. And this is, remember, at time t equals 0, the initial shape. And the same thing at every point here, they have a different u, even though it's at the same time t0. So at each x there is different u, even though it is the same time t equals 0. Now this wave, if we let it go, if the pulse let it go, then it will move in the right as well and the left hand directions at a speed. Let's call this speed now c. Now in time t, let's say now as time passes, in time t, the distance covered by this wave in the transverse direction is given by speed times time, ct. And this is the distance the pulse moved, that is the energy moves in this direction or in that direction. It's not the displacement up and down. We are not talking about displacement. We're not talking about the energy or the pulse movement, propagation of the wave to the right or to the left. For example, if you have this point, on the string at t equals 0, this point, or if you put, let's say, a piece of paper, this piece of paper doesn't move to the right or to the left. It just pops up and down as time passes. So if you look at the other graph here, you see that at time equal t, the same point P0 now is not on the x-axis, as almost on the x-axis as we can see here, but it moves up. It pops, vibrate, oscillate up. Its new position is here. It's a new displacement, but its x coordinate stays the same. So it's this is the location or displacement of this point pt at time t. That's why we call it pt. Now, as we said, that the wave has covered a distance ct. Now let's compare this with the initial one at t equals 0. If we compare the displacement of this pt like that, we draw a line, and you see that the displacement, this displacement is the same like a displacement at the point at the x coordinate x0 equals to x minus ct, minus the distance covered. So they have the same displacement. This point is the same displacement as a point at a position x0 equal x minus ct. And the same thing applies if the wave propagates into the left direction. The same thing. The point on the opposite side will be having the same displacement like a point at x plus ct. And that gives us the general equation. U of xt equals f of x minus ct plus g, if we call the one on the other side g, of x plus ct. So we combine them together. And this gives you, as we have written here, one is uxt See, ux minus ct, this is at time t 0. This represents the first one because this is at time t equals 0. Alright, we could write it as if f as a function of f, x minus ct. So this is the part that travels to the right. The same thing for the section that travels to the left, and we combine them together to give us the general wave equation here. Uxt equals f of x minus ct plus g of x plus ct, exactly as we have started here, equation 1. Okay, now to clarify also, we give an example. As you can see here, let's have a wave with an initial shape that is given at time t equals 0. That is the initial shape of the wave. It could be like a string, it could be a sea wave. It's given at t equals 0. Then the displacement ux0 is given by a function, we call it b of x. It's given by this expression equals e minus x squared. So this gives the shape. It's like an exponential shape. So this is the shape of the wave equation at time equals 0, the initial one. As we discussed before, we are given the initial shape. Also, we are given second condition that the initial velocity equals 0, because like when you started, you hold the string, its initial velocity is 0. So we want to write the equation that represents this wave. Again, so we use the general solution as we put it, ux of t equal f of x minus ct plus g of x plus ct. Alright, so let's call this equation 1. Now the velocity of this wave can be found by taking the partial derivative of u with respect to t, time. So that's du dt, variables xt, equals df of the function x minus ct dt plus dg dt of x plus ct. Now we're deriving with respect to t. That's why the derivative will be multiplied by this one by minus c, as you can see, and this section will be multiplied by plus c. So this means at t equals 0, du dt x0, because t is 0, equals minus c f of dash of x, because that's becomes 0, so the derivative now is with respect to x, plus similarly c, this becomes 0, and this becomes g dash of x. Alright, so this equals to 0 because the initial velocity is given as 0. Now if we simplify this equation and we rearrange it, this gives us that c and c cancel, so f dash x equals to g dash of x. And if we integrate, this is a solution, f of x equals g of x. There could be other solutions, for example, but this is a simple solution, f of x equals gx. Alright, so we found this, that f of x equals g of x. But we know that at t equals 0, as we see from equation 1, u of x 0, we sub 0, right, equals to f of x, because this becomes 0, plus g of x, because this also becomes 0. So ux0 equals f of x minus c times 0 plus g of x plus 0. That gives us f of x plus g of x. So this is the shape of the wave at time 0. But that's given from the beginning, as we can see. You go back to what we are given at the beginning. At t equals 0, this shape ux0 equals to b of x equals e minus x squared. This is the initial shape. So we write this equals to b of x equals e minus x squared. But as we saw here, f of x equals g of x. So this means that f of x plus f of x, because they are equal, equals to e minus x squared. So this means 2 twice. So we got 2 f of x, because we are adding, equals to e minus x squared. Divide by 2, each side. So this means that f of x equal to g of x, because that's g of x, equals half e minus x squared. Now we got this also condition. So the wave equation now is obtained by substituting in equation 1. So u of x of t now equals to half, we call it b instead of f because that's what we use there, x minus ct plus half b x plus ct. Now we are given that's equal to e minus x squared. Replace x here with x minus ct squared plus again here x plus ct squared. So the general equation becomes of this 1D wave function is given by ux of t equals half e minus x minus ct squared plus half e minus x plus ct squared. And if we plot this function and the initial function, we will see how the shape of the wave, the initial wave, has split into two waves, smaller waves. One moves to the left and one moves to the right. Okay, now if we draw the initial shape of the wave at t equals 0, it's an exponential function. So it will look like this on this side and like this on this side. So this axis is u of x of t. So it's just one wave. As we can see, its amplitude is 1. So this is at time t equals 0. Now, after some time, short time, the shape will be like this. So the wave has split into two smaller waves, and each one travels in different directions. As we can see, this is based on the equation that we found before for this function. And after, as t increases further, this wave keeps moving to the right and to the left again. So that's it, folks, for this time. Thank you for watching. Please subscribe.
بس لا يا